In 6.7, we're going to talk about the dot product, which is an operation that happens between two vectors. And kind of taking a step back, whenever we did vector addition or vector subtraction and scalar multiplication, the result was always a vector, right? So the vector was the solution or the product from adding and subtracting. However, when we do a dot product between two vectors, the result is going to be a scalar. It's just a number. So keep that in mind. Knowing what type of answer to expect is very important. So the result from addition, subtraction, and scalar multiplication comes out to be a vector. However, when doing the dot product, the result is a scalar. Okay? So, what is the dot product? The dot product requires two vectors, so v and w. And here we have ai plus bj defining v, and ci plus dj defining w. So a, b, c, and d are scalars or just real numbers. So the dot product is represented like this. V dot w. This is not a multiplication. It's not v times w. I know we're used to writing the product or the multiplication between two things with a dot in the middle. So this one is a little bit of a thicker dot, a little bit darker, wider. So try to keep that in mind. So the definition is as follows. So the dot product between v and w is the same as the product of the horizontal components plus the product between the vertical components. Okay, so again, the dot product of two vectors is the sum of the product between the horizontal components and their vertical components. Okay, so it's kind of simple as long as you understand from the beginning what you're supposed to do. So let's do a couple examples. You're given the following vectors, v and w, and we want to find the following dot products. So v dot w, it's the same thing as 5 times -3 plus -2 times +4. So this right here is the horizontal components, I guess the x direction values, and then these are the y direction values, if that makes sense. So if we do that, we get -15 plus -8. So -15 minus 8 is going to be -23. Okay? That's the solution. -23 is the solution between the dot product of v and w. Now let's do part B, which is the dot product between w and v. So we'll do the same thing. -3 times 5 plus 4 times -2. This is -15 plus -8, and their sum is -23. So that's kind of neat. The order in which you do the dot product in doesn't change the product, the solution itself, so the outcome. And last, we'll do the dot product between v and v. So b dotting itself. So that'll be the horizontal component times the horizontal component plus the vertical component times the vertical component, and we get 25 plus 4, and that comes out to be 29. So that is the answer for the dot product between v and v, the dot product between w and v, and the dot product between v and w. Let's talk about a couple properties of the dot product. So say that we have three vectors, u, v, and w, and then we have a scalar p, just a number p. Then the following is true. U dot v is the same thing as v dot u. We just saw that in the previous example, and it's true, right? The order in which you dot the vectors, it doesn't matter. It's true in either direction. Then, if you do the dot product of the sum of two vectors, it is the same thing as u dot this first plus u dot the second vector. Kind of like a distributive property, it behaves very similar. A zero vector dotted with the vector v is equals to 0. Remember, the dot product comes out to be a scalar. So all of these answers, or the solutions, are a scalar. Then we have a vector dotting itself. It is the same thing as finding the magnitude of that number and then squaring it. Okay? Then if we have a scalar multiplying a vector and then dotting a vector, it is the same thing as doing the dot product first and then scaling it, or scaling the one vector and then dotting it with the other. It is all equal to the same thing. Now, there is a different formula for the dot product. So say that you were given two vectors and they are non-zero because we want to exclude the zero vector. So theta now is the smallest non-negative angle between them, between these two vectors. Okay? So we're assuming that they are coming from the same initial point. So the dot product between the two is equal to the magnitude of the first times the magnitude of the second times cosine of the smallest angle between them. Okay? So that is one way to figure out the dot product between two vectors. Now, since you noticed in the previous formula, there is a theta. That means that we could solve and figure out what is the angle between these two vectors. So, given the same information, here's the formula. Let's solve for theta. So, since this right here is all being multiplied, we can divide both sides by it, and we get something like what we have here. Then we have cosine theta equals that, and if we solve for theta, then we get cosine inverse of the dot product between v and w divided by the product of their individual magnitudes. Okay, let's do an example finding the angle between vector v and vector w. So, as we said, The formula to find the angle is going to be cosine of the angle and that is equal to the dot product divided by the magnitude of each, and then a multiplication of it. So we got a couple of things to find actually, and if this is one of the first times you do this, then I suggest let's do it in parts. So let's find dot product between V and W. So remember, the dot product is the product of the horizontal components, and so plus the product of the vertical components. So we get -3 plus -8, -11, okay? And then we can find the magnitude of each vector on their own. So the magnitude of V, so the square root of 3 squared plus -2 squared, and that comes out to be 9 plus 4. So square root of 13, and then the magnitude of W, same thing, square root of -1 squared plus 4 squared. This comes out to be 1 squared plus 16, so square root of 17. So now I have what I think it's all the components, right? The dot product, the magnitude of one vector, and the magnitude of the other. So now I am ready to just plug in those values. -11 divided by square root of 13 times square root of 17. And maybe I'll just get that dot out of the way so it doesn't look like I'm doing a dot product or anything like that. You just know it's a good old multiplication. It's a product between two numbers. And so -11 divided by, and I can do one radical for those two. So the product between 13 and 17 comes out to be 121. Oops, I'm sorry, 221. And what we have right now, let's see, is that this is equal to cosine of theta. Well, I want theta, not cosine of theta. So what I'm going to do is do cosine inverse of this. Okay. Put that in the calculator. And since we don't see any pi or anything around here, make sure your calculator is in degrees. And so theta is then going to be roughly 137.7 degrees. Now let's talk about parallel vectors. So vectors that are coming from the same origin or the same initial point and are pointing in the same direction. For example, the angle between them is 0. Here we have angle V and angle W, or vector V and vector W. They're pointing in the same direction, so the angle between them is 0. However, if they had the same initial point, but they were pointing in different directions, then the angle between them is going to be 180 degrees, right? This right here is theta. And that's what we're talking about, pointing in opposite directions and then having an angle that represents that. Then orthogonal vectors are going to be two vectors that whenever we look for the angle between them by performing the dot product equals 0. So orthogonal vectors, whenever you take the dot product between them, equal 0. So since the 0 vector dotting with any vector equals 0, we can say that the 0 vector is orthogonal to every vector v, or just any vector really, because you're going to dot it with whatever we call that vector, and it's going to come out to equal 0. Well, therefore, vector 0, or the 0 vector, is orthogonal with everything. Now let's talk about something very, very interesting, but a little bit confusing. So, vector projection is the following. So, you have vector v and w, and they are non-zero vectors. So, the vector projection of v onto w is defined by the following. So, this definition, it says the projection of v onto w is given by the dot product between v and w divided by the magnitude of w squared times vector w. Okay, so that is the formula, if you will. Now, what does a projection mean? So, if you look here in the picture, I have vector v and vector w, and you're pretty much looking above from it, and you are creating this right angle vision from above, and so you're trying to figure out how much is one vector pointing in the direction of the other. So the projection of v onto w is the shadow of v on w. Okay, so you're looking and you're trying to figure out what is the distance from here to here, right? How much is vector v pointing in the same direction as of vector w? Okay, so that is one way to look at it. If the answer is positive, or in this case, we're talking about the angle between them. If the angle between the two is between 0 and 90 degrees, meaning that at least they're pointing in the same direction, then you will expect to find something like this. However, if the angle is greater than 90 degrees but less than 180, then you're going to have something like this, right? Where the vector is actually pointing in the opposite direction somewhat. Therefore, the projection is going to be a negative vector. Okay? Hopefully that makes sense. So let's do one of these problems, right? So we want to find the vector that is the projection of v onto w. So the wording matters very much, because I'm looking for the shadow of v on top of on top of the vector w, right? And if it was the opposite direction, I would be looking for the shadow of w onto v. Okay, so whichever one comes first is the one that's casting the shadow on the other vector. So let's see if this helps, and let's try to plot those two vectors first to get a good idea as to where they are. Okay, so if I look at vector v, it goes 1, 2, 1, 2, 3, 4. So that's right here. And then vector w goes 1, 2 to the left, and then 6 upwards. So let's see if we can make that straight line happen. Nope. Kinda. Okay, so this was w and this was v. So if I'm looking at vector v and I'm looking at from this direction, for example, so that it casts a shadow, that it makes a right angle with vector w, we'll get the following. So here's the solution, I guess. The projection of vector v onto vector w is going to be the dot product between the two. So let's write that down. Times the magnitude squared, well, divided by the magnitude squared of w times vector w. So let's find those separate pieces all together. So dot product between v and w. So we have 2 times -2 plus 4 times 6. So -4 plus 24, that equals 20. Magnitude of w, but then squared would be the same thing as this. And so that is going to be essentially -2 squared plus 6 squared. So 4 plus 36 equals 40. Okay, so I have this value, which is that one and that one. So all that we have to do now is multiply to vector w. So 20 over 40 comes out to be 1/2. So 1/2 times vector w is going to be the following. So 1/2, I guess we'll write down what that is. So 1/2 times -2i, that's a vector, plus 6j. So it's going to be -i plus 3j. So this right here that we just got is equal to the projection of v onto w. So if I was to kind of draw that out, it says 1 to the left and 3 units up. So somewhere right there. And so we get a new vector here. And okay, drawing a straight line is very hard, it seems. And the idea was, I think I explained it wrong in some way, is that I'm looking at the vector in this direction, and it makes a right angle with vector W. So that is how much is actually pointing in that direction. So I guess that blue line should be on vector W right here. I think it's more accurate than that right there off to the side. Okay, I hope you can see that. So this right here in the blue is the same vector that we found right there, and that's how you find a projection. A projection is just a bunch of other components put together, but the idea is this, right, is how much, if you're trying to cast a shadow from one vector onto the other so that it makes a 90-degree angle with said vector, well, what is that vector here coming from the origin? Well, this is how much the shadow of V is onto W. Now, let's talk about the components of a vector, and not really in terms of magnitude and direction. Those are basic components, but then there's a farther breakdown, and we're looking at it from the point of view of the projection. Say that we have vector V and W, and they are non-zero vectors. So vector V can be expressed as the sum of two orthogonal vectors. Okay, that's fine. V1 and V2 are those two orthogonal vectors. V1 is parallel to W, and V2 is orthogonal to W. So let's try to copy that picture from before, and although it's not that pretty, I think it's going to work. So let's kind of bring it in here and make it larger to explain it better. So we already talked about one of these two, V and V, the other one being W, right? So this is the result. The blue line is the projection of V onto W, which is this right here. We say V1, we're assigning it some value, right? We're naming it something, is equal to the projection of V onto W. And that is equals to the definition that we just showed above. Okay, now V2, or that orthogonal vector, is equal to the original V minus V1. So what does that mean in pictures? Well, I'll tell you what that means. Here is the vectors that I was telling you about. This vector is orthogonal to W, so this is V2, and my blue friend right here is vector V1. Okay, so V1 is the blue guy, V2 is the red, and V is this one right here. Okay, so graphically, that's what's happening, is that you find the projection, you assign the projection some name, and if you do vector V minus vector V1, you end up with this vector right here, and that's vector V2. So the sum of those two vectors v1 and v2, which happen to be orthogonal to each other, adds up to vector v. Okay, so the same problem can be asked in many different ways. Okay, however, if you understand all these different components, I think you should be all right. Let's do an example and figure out those different components, right? So we're going to decompose, in other words, vector v into v1 and v2, right? And we're told that v1 is going to be parallel to vector w, so they're pointing in the same direction. And v2 is going to be orthogonal to w, meaning their dot product would equal 0, or the angle between them 90 degrees, right? So let's go ahead and do that. And the way we do that is going to be by doing a projection. So that projection is going to be equals to the angle, to the vector v1, and that is the projection of v onto w, and the definition is dot product of v and w divided by magnitude of of w squared times vector w. So let's do those things separately. So v dot w is the same thing as 2 times negative 2 plus 4 and 6. I think those numbers look familiar. We already did them. So negative 4 plus 24, that equals to 20. So that is the product between the two. The magnitude squared of w is going to be 4 plus 36. That is equals to 40. So we have 20 over 40 times vector w. So that is 1/2 times negative 2i plus 6j. And then all of that comes out to be negative I plus 3j. And remember, this is equals to the projection, or vector v1. Vector v1 is the vector parallel to w. Now, if you remember, or go back to the previous point, we said v2 is equals to v minus v1. Well, we can definitely do vector subtraction or addition. Algebraically, it's easier to do it than geometrically or graphing it, I believe. So, what is v? Well, v is 2i plus 4j minus, and it's better to put things in parentheses so that we don't mess up. Right, this is v minus v1, and we just do the following, right? We do difference in the horizontal components, and then just put the I plus the difference in the vertical components, and then add the j at the very end, and we have 4i plus j. So that is our vector v2. So v2 is orthogonal to w. I think I made a mistake. This right here should have been a 2. So 2 plus 1, and this should be a 3. Okay, so 3i plus j, right? And if you need to check your work, remember that v1 plus v2 should go back to give us v. So in essence, we found the decomposition of vector v, right? Here are the two vectors that add up to it. Okay. Next, let's talk about the definition of work. What is work? So work is denoted by the letter W, and it is done by a force moving an object from point A to point B. Okay, so the simple definition of work is force times the vector AB, or the vector from A to B. Okay, if you're given the force, which is a number, how much something is pushing something, that's it. That's all you have to do. Plug in that number times the force. Well, plug in the number times the distance, sorry. Now, arguably there's an easier way to do it, or there is an alternate formula, which is this right here. The alternate formula is that you multiply the magnitude of the force. If it's given as a vector, you would like to find the magnitude of it, multiply times the magnitude of that vector times cosine of theta. Well, here below is the breakdown. So magnitude of F is the magnitude of the force. How much force is being exerted? The magnitude of AB, or the vector AB, is the distance over which the constant force is being applied. How long of a distance are you applying that force to? And theta is the angle between the force and the direction of motion. Okay, let's do an example. A child pulls a sled along the level ground by exerting a force of 30 pounds on a rope that makes an angle of 35 degrees with the horizontal. How much work is done by pulling the sled 200 feet? Well, it's often suggested that it is good to draw a picture, right? So maybe here is a sled, and here's the kid. Right? I don't know. Here's the rope. And so when it says making an angle with the horizontal, here's the angle of 35 degrees, right? And the person is pulling this, and it makes a force of 30 pounds. So what definition do we use? Or how do we do it, I guess? Work is equals to the magnitude of the force, like numerically how much force is happening, times the distance, pretty much, times cosine of theta. So force, 30 pounds, times how long, 200 feet, times cosine of 35 degrees. All of this, assuming the calculator is in degree mode, has an answer of 4915. Okay, so the work done is approximately 4,915 foot-pounds. So foot-pounds is the unit for work. And that is everything from section 6.7.